All right, today we're going to start our Unit 2, and it's on linear systems. We've been doing a lot with linear the last unit, chapters 1 and 2. We're going to continue that and also expand a little bit. As a matter of fact, in the last unit we graphed a lot of lines and absolute value v's. We found domains and ranges and vertices, and we talked about transformation of certain functions. And all of that we talked about in the last unit will be the basis as we move on to systems. What exactly are those? And then we're going to continue and grow the system with our inequalities. So at the end of the day today, you'll be able to graph inequalities in two variables. You already know how to graph equations in two variables, linear and absolute value. We did that last week. And then we will also move into finding the solution of a system of equations using the graphing method. So here we go. Let's start with something nice and sweet, simple. We have y is less than or equal to 3x plus 2. This is obviously a linear equation. It's a linear equation because we see the slope and we see the y-intercept. And these are very easy to graph. So let's start by just graphing that line. Let's pretend this is not an inequality but an equation. So of course I'd go to my y-intercept. I would go y is 1, 2, 3 over 1, and that would be my line, right? However, this is not equal to, it is less than or equal to. So less than indicates a below or to the left. So I want my y to be less than that line. So logically thinking, less than would be down here. However, I want to test to make sure that's the right area. So I'm going to test 0, 0, which is right in the middle of that shaded area. When I say test 0, 0, basically I mean I want to put 0 in for x and 0 in for y and see if it makes a true statement. So if I put a 0 in for y and 0 in for x, then I will end up with 0 is less than or equal to 2. That's a true statement. So 0, 0 did make the inequality true. Therefore, it is part of the solution set. And if 0, 0 is a part of the solution set, so is every point on this side of that line into eternity, forever and ever and ever. So my question is, so the solution to this inequality are a bunch of, not numbers, but a bunch of ordered pairs. I need a set of ordered pairs because I need an x and a y to plug in to see if it's true or not. So the solution's not real numbers, it's ordered pairs. And how many solutions are there to this inequality? Well, this ordered pair would work, this ordered pair would work, this ordered pair would work, this ordered pair would work. I'm going to prove that to you. This would be the point 10, 10. I'm going to prove to you that, for example, that one would work. If we stuck a 10 into our original problem, we'd have 10 is less than or equal to 3 times 10 plus 2. 10 is less than or equal to 30 plus 2, 32. Again, true statement. 10 is less than 32. So there are an infinite number of solutions. There's an infinite number, but you can't just stop there. You've got to say an infinite number of ordered pairs found in the shaded area. You have to identify where those points are. You just can't say every point in the universe, every real number point, because this point doesn't work. If I plug that in, it would not make a true statement. Or if I plug this x line in, it's only the ones in the shaded area. What if we're graphing from standard form, which is what this is? Many times in standard form, especially if these two numbers are factors of this number, if that's the case, then it makes it very easy to find your x-intercept by plugging a 0 in for y, find your y-intercept by plugging a 0 in for x. If we stick a 0 in for y, this whole term will go away, and we're left with 3x and a 12, so x has to be 4. We stick a 0 in for our x. This whole term goes away. And I've got a 6y and a 12, so the y would have to be 2. And once I had my two intercepts, 1, 2, 3, 4, oh, I missed it. 1, 2, 3, 4, and 0, 2. Now I've got lines and points. I can draw the line between them. However, notice that this is not a less than or equal to. It's just less than. So I'm going to draw a dashed line in the same way when we're graphing on a number line, we use an open circle. This is kind of like an open line. Again, I would think since this is less than, the original problem is less than, I would assume it's going to go down below that line, but I'm going to test 0, 0 just to be sure. If I stick a 0 into the original problem for x, I'll get 3 times 0 plus, now stick a 0 in for the y. That needs to be less than 12. Let's see if it is. 0 plus 0 is 0. It's less than 12. That's very true. So therefore 0, 0 works, and all of his buddies, any ordered pair over here into eternity would work. So if I'm asked to list 3 ordered pairs that are part of the solution, I can pick anything in this shaded area. This one right here. That's the point, 2, negative 3, if I'm reading that correctly. I can pick this point right here, which is negative 10, 0. I can pick this point right here, which is negative 1, negative 9. So pick any point you at all in that shaded area, and you've got you an answer, part of the solution. Well, what if I didn't give you a graph? Instead, I just gave you an inequality and asked you, is this ordered pair in that shaded area? Well, it's very simple. You just plug that in and see if this x and this y make the statement true. So in this case, in number 1, I'd have 5 times 0 minus 2 times negative 4 is less than or equal to 6. This is going to be 0. This is going to be 8 is less than or equal to 6. Is that true? No, that's not. So this is not part of the solution set. Would not be in the shaded area. How about 2, 2? Well, let's plug it in. 5 times 2 minus 2 times 2 less than or equal to 6. 10 minus 4 less than or equal to 6. 6 is less than or equal to 6. That's true because it is equal to. So yes, this is part of the solution set. Let's do one more. Negative 3, 8. So let's stick a negative 3 in for x. And I will put in an 8 for y. And let's see if indeed that is less than or equal to 6. This will be negative 15 minus 20, minus 16. Minus 16 is less than or equal to 6. This is going to give us negative 31 is less than or equal to 6. Very, very true. So, yes, that would be part of the solution set. All right? So if you're asked if an ordered pair is part of the solution set, just plug it in and see. Tells the truth if it satisfies it, and yes, it is part of it, the solution set. Now, what if you have an equation like this? Y is less than or equal to negative 3. Your first thought is going to be, well, there's one variable, therefore aren't I just doing this on a one-dimensional number line? Well, not exactly, because they've given you a coordinate system to graph it on. And that should give you a hint that this is a line, not something you would graph on a number line, even though there's only one variable. So you kind of know that by context, just like in English, you have context clues. Well, the context clue here is that they've given you an ordered pair. So you need to come up with an x and a y out of this equation. Well, I don't have any x's, so I could write that as 0x minus 3. Oh, now it's coming clear. This is my slope, which is a horizontal line. This is my y-intercept. So I'm going to go to my y-intercept, and I'm going to draw a horizontal line. And it's equal to right here, so it's going to be a solid line, and it's going to be a horizontal line. Whoops, missed a little bit, you got the idea. It was on a line. Then the question is, I want it less than or equal to that. So I would shade down. It's below, less than. If I check 0, 0 in this case, this will probably, it should be a liar. And yes, it would be, because the only thing I have to plug in would be the y. And 0 is not less than or equal to -3. That is not true. So I know I do not shade up there. What if my equation looks like this, or my inequality? X is less than 2. This one is just downright weird, because I don't have a y that I can put in y equals x plus b. All I have is an x. That's all I have. All I know is that my x is going to be 2. So I'm going to draw it, so I know my x is going to be 2. So I'm going to go put a 2 at my x. And then, this is so weird. Weird ones are the ones that have no slope, or undefined slope. Oh, those are big vertical lines. So I should have made that dashed, because it's just less than. So we'll dash that bad boy. And then I want less than that. Less than would be to the left. So in this case, if I tested 0, 0, he would work, because he is part of the solution set. So watch for those, that type of different. All right, let's talk a minute about a word problem here. We're not going to solve the problem. We're just going to write an inequality. You have $20. You have a $20 phone card. Calls made using the card cost 3 cents per minute to destinations within the United States, and 6 cents per minute to destinations in Brazil, where your brother's going to college. Write an inequality describing the number of minutes you can use for calls to both the U.S. destinations and to Brazil. Well, what I'm looking for is number of minutes. So I'm going to let X be the minutes that I can call the U.S., the minutes I can call people in the U.S. I'm going to let Y be the minutes I can call to Brazil. I know the cost of each of those, and I also know the cost, the amount of money I have. I only have $20. So the cost for each of these X's going to the U.S., the cost is going to be 3 cents per minute. So 3 cents times however many minutes I'm talking United States, plus 6 cents per minute to Brazil. So 6 cents for every minute I talk to Brazil. That total cost needs to be less than or equal to $20, because that's all I have is $20. And I do put or equal to because it could be 20. It doesn't have to be less than 20, it could be 20. And that's all that you're required of here is just to write an inequality. Write an inequality describing the situation. And that's what we did. All right, now let's move to inequalities. Absolute values, not a problem. You know how to do absolute values. You did them all last week. We can use our whole AH and K business. So I have Y is greater than or equal to the absolute value of X minus 1. Well, if I put plus 0 here, then I know that my vertex is negative HK. So my vertex is 1, 0. Remember to put that in the center of your T-chart. Go to the left one, to the right one. I'll plug a 0 into the original equation. I will get 0 minus 1 is negative 1, but the absolute value is 1. If I stick a 2 in for X, 2 minus 1 is 1. The absolute value is 1. So it got me 3 points. 0, 1, 1, 0, and 2, 1. Now, I know I'm going to write a V, because that's what all absolute values do. However, this is not greater than or equal to, it is just greater than. So I'm going to draw me an open, if you will, an open V, or a dashed V, because it can't lay on the line, but it can go right up to that line. Now I need to know, am I going to shade, is the solution set everything outside the V or inside the V? Well, let's use our old 0, 0 and find out. Because if he works, then everybody outside of the V will work. So if I plug 0, 0 into the original equation, I will get 0 is greater than the absolute value of 0 minus 1. So 0 is greater than the absolute value of negative 1, which is 1. That is not true. 0 is not greater than 1. Therefore, 0, 0 is not part of the solution, nor are any of his buddies. Instead, all of these points in here are going to be part of the solution set. Any of these points in here are plugging in to make it work, make it a true inequality. You'll remember from last week, we'll make our V maybe a little more complicated, but it's not a big deal. We still know we're still going to use our HK. So my vertex is 1, negative 4, just right in the center of my T-chart. I'm going to go to the left, I'm going to go to the right. I'll plug in 0 in for x. 0 minus 1 is negative 1, but the absolute value is 1. Times negative 2 is 2. Minus 4 is negative 2. If I go in and plug in a 2 for x, 2 minus 1 is 1. 1 times 2 is 2. 2 minus 4 is negative 2. Got me 3 points. 0, negative 2, 1, negative 4, and 2, negative 2. I know it's going to be a V because it's an absolute value. So I'm going to make sure, should I have done a solid? Oh, yeah, I left out. Yes, I am going to do a solid because of this 4 equal to right there. So solid V. Let's see if I'm going to shade inside or outside that V. Let's test our little friend, 0, 0, and see if he gets to play this time. So I'm going to stick 0, 0 into the original equation. So 0 is greater than or equal to 2 times 0 minus 1 minus 4. 0 is greater than or equal to 2 times absolute value of negative 1 minus 4. 0 is greater than or equal to 2 minus 4, which is negative 2. And that is very true. 0 is greater than that. So therefore, 0, 0 is part of the solution set, as in this point, and this point, and this point, and this point, and every point inside of there. This guy here would not be part of the solution set. He'd make a false statement. This guy would make a false statement. It has to be the shaded area inside, or the ordered pairs inside the shaded area. All right. That's your slide there for some reason. So now let's switch gears a little bit and ask, what if we're asked to graph a system of equations? And notice we've gone back to equations. We've got equal signs. We're back to equal signs, so we won't have any shading. What am I asked to find if I say solve this system of equations? Well, basically what I'm looking for is an ordered pair. So if I plug this x into here and here, and I also plug this y into here and here, both of those sentences, both of those equations will be true. So I'm looking for that ordered pair. Well, where would I find that ordered pair? Well, let's think about this. These are the same two problems. Let's graph them and see what it looks like. So this first equation, I'm going to go to 2. And I'm going to go down 1, 2, 3 over 1. And you will want graph picker for this part of your assignment because you have to be really accurate or you won't do it. You won't end up in the right place in your graph. The second equation, I'm going to go to negative 3. And I'm going to go up 2 over 1. Up 2 over 1. So this line will be right here. And so I want to know which point would make both of those equations true. What point is on both lines? Well, this point right here, it satisfies the blue line, and that point right there also satisfies the green line. And that point happens to be 1, negative 1. So in this case, there is only one solution to this problem. It's not an infinite number. There's just one solution. I should be able to put this ordered pair back into both problems up top, and it should make them true. Let's see if it does. So here's my y, here's my x. So let's put it into the first equation. Negative 1 is negative 3 times 1 plus 2. Let's see if that works. So negative 3 plus 2, negative 3 plus 2 is negative 1. Beautiful. So it works in that one. Let's see if it works in the second one here. I've got, so my y is negative 1, so negative 1 equals 2 times my x, which is 1, times 3. Negative 1 equals 2 minus 3, 2 minus 3 is negative 1, bingo. So I know I'm correct because that ordered pair, when I plugged it in, made both statements true. So I have solved the system of equations by finding one solution that fits them all. So that's the general idea of how to do it. We're looking for an intersection. But sometimes the equations themselves are not written in a way that's real conducive to, boy, that's easy to graph. So these two are both in standard form, but notice that this 3 is a factor of 24, but negative 10 is not. So that's going to be hard to find the x and y intercept. Same on the first equation. This 7 will not go into 17. So I've got to find another way, or we could solve that and then graph fractions, or how about let's just turn them into y equals mx plus b. Let's turn this first equation, y, let's take this over, and that would be negative 7x minus 17. The next equation, I would have negative 10y equals, take the negative 3x over, and divide by negative 10. So y is going to equal a positive 3/10 x minus 4 into both of those, no, 2 into both of those, and get 12/5. So I'm going to grab this one, and I'm going to grab this one. Now, this one's going to be hard for me because I do not have space on my graph. So let me see if I can get space on my graph. Hang on just a minute. All right. I got another piece of graph here because this would all fit. So let's go back to graphing this blue one. So I'm going to go to negative 17 on my graph. I can't go down 7. It's negative 7 over 1 for my slope. I can't really go down 7 from there. But remember, that also equals 7 over negative 1. So instead, I'm going to go up 7 and then to the left 1. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, and to the left 1. So there's my line there. And I'm going to use this to try to make my line straighter. Then the second equation, let's do, that was that one. Now let's do this one. This negative 12/5 is a negative 2 and 2/5, right? So I'm going to go to negative 2 and 2/5, and 2 and 2/5. And then from there, I'm going to go up 3 over 10. So 1, 2, 3 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this line is going to be up to here. Now at this point I have a decision to make because my graph is not accurate enough. So you probably want to use a straight edge. This is my intersection section, and I just kind of have to guess at that. I'm going to guess that point, or estimate, I shouldn't say guess, estimate. That point is at negative 2.5, negative 2.5, and then down 1, 2, no, excuse me, negative 2.5, and then down 1, 2, 3.5. Okay. So sometimes you look at fractions, but obviously yours may look a little bit different than mine because of my thickness of my line, if I was straight, there's all kinds of things that go into it. So next week we'll be talking about methods that are much more accurate than the graphing method. But for now, that's what you'll do on your assignment today. Just graph those. Same thing here. I would solve each of these for y, put them in y as an x plus b. So let's do that real quick. So this first one's going to be negative 7y equals negative x plus 6. Divide everything by negative 7. So y equals a positive 1/7x plus 6/7. Graph that. And for the second equation, this one, let's go down and do 21y equals 3x over minus 18. And we saw divide everything by 21. And y equals 3 over 21, which would be 1/7, minus, put a 3 into both of those. Okay, so that's interesting. Wait a minute, let's look at what's going on here. These guys have the very same slope. They just have different x-intercepts. So that means they're going to be parallel. Watch how this works. I'm going to go to 6 to graph this one here. I'm going to go to 6/7, which is almost a whole. And I'm going to go up 1 over 7. So the line is roughly going to look like this. And then the second one, I'm going to start at, let's see, where are we down here, at a negative 6/7, which would be about here. And I'm going to go up 1 over 7. And this line is going to, it would be much better if I was more exact, but they are the same slope. So the question is, if you get two equations that have the same slope, how many times are they going to intercept? They're never going to touch each other. So there is no inequality, no ordered pair, because this one right here, it's not going to make the green line good. This one up here, this point right here, this 2, 1, it's only going to satisfy and make the green line true. It's not going to make that purple line true. It's not part of the purple intercept. So therefore, this inequality has no solutions. There are no solutions. There is no ordered pair that you could plug in for the x and the y in both of those equations to make them true. There are none. So that would be a no solution. So look for parallel lines. All right, let's look at this equation. I don't want that. I don't want that fraction. So I'm going to multiply by the denominator on both sides of this guy to get rid of the denominator. So I'm going to multiply this side by 2 and this side by 2. So this equation will turn into, the 2 will cancel, so I'll have 5x minus 2y equals negative 8. Okay, so let's now, let's put them in slope-intercept form maybe. It's just going to be kind of hard. But wait, I'm noticing something here. I'm noticing something. This is exactly the same. This is exactly the same. So that side of the equation, those will be the same thing. How could in this equation that equal a 4, and in this equation that same thing equal a negative 8? It can't. If these two pieces are the same as these two pieces, then the answers to those two have to be the same too, and these are not. So I'm going to stop right there. I'm not going to go through the hassle of graphing them, because this tells me that there is no ordered pair that's going to make this true. No, I'm lying. No, that's right. That's right. Yeah, because they're going to be parallel again. Okay. So the parallel lines there as well. Sometimes we'll put together a absolute value with a line. no big deal, we're still gonna just graph to where they intersect. So this first V, the vertex is gonna be the 1, 0. You go up 1, down 1. Let's take a 0 in, that's going to be 1. Let's take a 2 in, that's going to be 1. So 0, 1, 0, 2, 1. So this is the absolute value. Again, you want to go for accuracy, so use your graphing paper and a straight edge. This second equation, I'm going to go to 4. And down 1 over 1. So this is a line. And I'm looking for where they intersect. I'm going to go back. This was totally not good. They intersect right there. So if I were guessing, I would guess that point is at maybe 2 1/4. And up maybe 1 3/4. Again, you may get just the 20.2, excuse me, yeah, 2, 2. You graph yours, your graph's a little bit different. So graphing is not an accurate way. It gets you close to what the solution is, but I would have to start testing these to see which of these were right. I'd have to start plugging it in to say what's going to make that true. Let's just try the 2, 2. If I put a 2 in here equals 2 minus 1, 2 equals, that's not going to work. So 2, 2 is not the solution because it didn't even make this top one true. So anyway, on these then, where you're graphing to get a point of intersection, you may get a little off from me, and that is okay. It's not a problem. All right, one last thing here, I think. We have how we're going to put this in. We're going to actually solve this one. During a calendar year, a state trooper issued a total of 375 citations for warnings and speeding tickets. Oh, speeding tickets, sorry about that. Of these, there were 37 more warnings than speeding tickets. How many warnings and how many speeding tickets were issued? Well, if there were 37 more warnings than speeding tickets, I'm going to let T be the number of tickets, speeding tickets. And 37 more than that is going to be warnings. So T plus 37 is going to be warnings. And he issued a total of 375. Those combined. So if T of them were given tickets, and T plus 37 were given warnings, that should be a total of 375. And notice that this question does say how many speeding tickets were issued and how many warnings were issued. So we need to go in and solve this. So 2T equals, I'm going to come over here and take 37 away. And that's going to be 338. So T equals 1, 6, 9. Is that right? 169 twice, 18, 13, 338. Yes, that's correct. And T was my speeding tickets. And then my warnings, I would just add 37 to that to get my warnings. So 169 plus 37 in my warnings. And that's going to be 16, 10, 206 warnings. And let's just double check. Are these two numbers going to add up to the how many total did we give? We did 375. Let's see. 9 plus 6 is 15, 3, 1, 7. Yeah, we did add up. So we're good to go. All right, I'm done. We'll need some graph paper, as I said, as I thought. So have fun.
See you next time.